My name's Shane Skinner, and I'm a technical marketing engineer with the Integrated Electrical Systems segment of Siemens Digital Industries Software. And today we will be covering the topic of integrating electrical and mechanical harness design. To start off with, I would like to explore why electrical and mechanical integration is necessary. With advances in technology comes demand for more complex electrical and mechanical designs. On their own, this complexity provides significant challenges for each respective design team, but when the end product is electromechanical in nature, such as an electrical wire harness, mechanical and electrical designers now have to account for challenges across both domains. The mechanical designers need to verify the physical space constraints of the harness. Once the wiring is finalized, how will the bundle thickness be affected? The electrical designers need to ensure the correct circuit behavior, which requires voltage drop analysis and fuse sizing calculations, that is dependent on real-world wire lengths. How can these wire lengths be obtained? The harness designer needs to reproduce the 3D harness topology in 2D and combine it with the electrical data. If the 2D harness is just a derivative of the 3D harness, why should it need to be recreated from scratch? With the MCAD integration supported by VeSys, we address these challenges. A design flow incorporating VeSys supports collaboration and concurrent design. Customers are able to design physical harnesses in their MCAD tool of choice, while the electrical and harness designs are done within VeSys. The mechanical designer defines the harness geometry and fixtures, along with reserving space in the vehicle or machine. The electrical designer, using VeSys Design, masters the electrical content for the system, creating the needed wiring diagrams and conducting analysis. Here, the mechanical and electrical disciplines can work independent of each other, but can easily pass data back and forth as it becomes available. The harness designer, using VeSys Harness, combines the MCAD and electrical data to fully define the electromechanical harness product. These interactions enhance the visibility between the Ecad and MCAD domains, supporting the co-design of mechatronic products. Having a better understanding of the impact electrical and mechanical specific decisions may have on the other domain is critical to the overall design quality. In addition, the data exchange supported by VeSys eliminates the need to manually transfer data between the tools, saving considerable design time and potential for manually induced errors. We will be going more in-depth on these exchanges during the demo. All of the integration capabilities are enabled via a combination of our bridges framework and adapters, which handle the exchange of information between MCAD tools and VeSys, and our plugins, which are developed using the MCAD application's APIs and deployed within the MCAD products. In return, this ensures a seamless integration of the data between the tools. VeSys supports integration with Creo, NX, Solid Edge, SolidWorks, and CATIA V5. VeSys and SolidWorks can exchange files natively, while plugins are available for the other MCAD solutions to manage the import of VeSys data. The Siemens tools, NX and Solid Edge, support a unique capability called Connected Mode. The NX and Solid Edge Connected Mode data exchange enables real-time data import and export, as well as cross-highlighting for ease of use and analysis during wiring and harness design. The functionality automatically switches between wiring mode and harness mode exchange as needed within the same application. Any selected objects in NX or Solid Edge will be cross-highlighted in your diagram, and vice versa. For example, selecting a wire in VeSys will cross-highlight the corresponding shortest route path and the devices in NX that the wire connects to. Available objects include connectors, devices, wire bundles, splices, wires, multicores, clips, grommets, and so on. For the following demo, we will be utilizing Connected Mode to handle the exchange of data between VeSys and NX. Now we will be covering the various ways in which VeSys can integrate with an MCAD design. For this specific demo, we will be using NX for our MCAD environment, and will cover the bidirectional transfer of data between VeSys Design, VeSys Harness, and NX. In the first half of the demo, we will focus on the exchange between our wiring data in VeSys Design and physical harness data in NX. The wiring information from VeSys will be bridged out to NX as a wiring PLM XML file, utilizing connected mode. Once the data has been exported to NX, connectors will be auto-assigned and wires will be auto-routed. Here we have the MCAD design open in NX and wiring design open in VeSys. As can be seen in the electrical connection and electrical component navigator of NX, there is no electrical content, only the bundles and connectors that have been added by the mechanical designer. Connected mode is established between both tools with the push of a button, enabling the real-time import and export of the wiring PLM XML file. The bridge filter allows us to select which harness designs we are exporting to. In this case, we will be using the single driver side door design. The report indicates the number of connectors, splices, and wires passed to NX. The electrical component and electrical connection navigators are now populated with the data from VeSys. We will auto-assign connectors by part number, but it's possible to make the assignment based on any attribute. We will then manually assign any remaining components, in this case, the 3 splices. Then, finally, we will also auto-route our wires at the component level. We successfully passed the electrical data from VeSys to NX with the push of a button, facilitated by connected mode. The mechanical designer had all the necessary data required to auto-assign connector part numbers as well as auto-route wires. This saves the mechanical designer a considerable amount of time, avoiding the error-prone task of doing it manually, and also helps ensure the connectivity is an accurate representation of our VeSys-created wiring diagram. Now that the wires have been routed in NX, they have accurate lengths according to the physical routing. This is valuable information for electrical designers who can utilize it to conduct additional analysis and further verify electrical behavior. This time, we will pass data from NX to VeSys and also highlight the cross-probing functionality offered by connected mode. With the wires fully routed in NX, they now have 3-dimensional lengths. We will navigate to a wire in VeSys and take note of the cross-probing functionality as we do this. Reviewing the properties for wire 6N1382, there currently is no wire length defined. Finding the same wire in NX, it can be seen that it has a length of 952 after routing. Since we have already established connected mode, we simply need to import from NX. As with the export, an import bridge report is provided to indicate what has been brought in. Returning to wire 6N1382, it has been updated with its routed length from NX. This will allow the electrical designer to perform more accurate voltage drop analysis and fuse sizing calculations within VeSys. To further verify everything has come over correctly, we can use the cross-probing again. Individual objects, such as a connector, can be selected to highlight it in both tools. With a connector selected, the electrical connection navigator will highlight all related connectivity, providing a visual indication of how they are wired. Individual wires can also be selected to identify how they will traverse the harness in the context of the larger parent assembly. We pass the wire length information back to VeSys so the electrical engineer can verify the electrical design. We also made use of the cross-probing functionality to ensure the transfer of data was successful and provide a better understanding of the relationship between the electrical and mechanical designs. Wire lengths are necessary for important verification steps, including voltage drop analysis and fuse sizing calculations. Being able to analyze these in VeSys can help the electrical engineer to catch and fix potential issues early before they are propagated downstream, possibly even to production, where the costs in terms of time and money can be exponentially greater. For the second half of the demo, we will move on to the integrations between the 2D harness design in VeSys harness and physical harness in NX. We will start by importing the 3D topology from NX via the harness PLM XML file and flattening it to produce the 2D harness in VeSys. Then we will synchronize the electrical data from our wiring design in VeSys with the 2D harness. We have NX and VeSys open and will once again establish connected mode, this time to exchange the harness PLM XML file. A quick thing to note, there are no wires present in the incoming data from NX. Routing wires in NX is an optional step for harness integration. Since VeSys Design owns the electrical content and can synchronize with VeSys harness, it is dependent on how you want your flow to operate to determine if wires need to be present in NX before importing to VeSys harness. In this use case, only the 3D topology without wires will be brought over. When importing, a number of options are available. First, the type of import can be selected either to update the harness in VeSys with the option to preserve electrical content, replace all content, or only replace wires and multicores. Bridge options provide further control. The Import tab allows you to center and scale the harness as well as define margins to fit your desired border. The Auto Link tab controls how matches are made between external and internal harness data. The Translation tab controls both the translation of part numbers and codes, which influences how component data is updated during bridge operations. The Change Policy tab accounts for how differences are handled when bridging in harness data. The Harness View dialog provides a preview displaying the incoming 3D topology data and presents the flattening transformation options that can be applied before processing into the harness design. The appropriate face views have been assigned for the connectors based on part number. Since the NX data did not include routed wires, we still need to synchronize with our VeSys wiring design. Harness synchronization is done to get electrical data from the VeSys design passed into one or more harness designs, either to add electrical data to an existing bundle configuration or as the basis for a new harness design. Wires and splices are populated in the harness design, and splices will need to be placed accordingly, which will be our next step. In this use case, the harness designer received the full 3D topology of the physical harness without wires, and synchronized the 2D harness with the electrical data from our wiring diagram. Again, this is an instance where manual work is replaced by automation that enables correct by construction design. Bringing in the harness topology from our MCAD environment and electrical from the Ecad environment guarantees our harness design has all the necessary data from both sources. For the final step, we will place the splices in VeSys and use automation to calculate the bundle diameters. This data will then be returned to NX. We will also make some modifications to the splices within NX and return them to VeSys to briefly highlight that data exchange as well. Picking up where we left off previously, the splices imported from our VeSys wiring design need to be placed on the harness. This is simplified by the node position utility, which allows you to precisely control its placement relative to other objects on the harness. Examining the properties of our bundles, they don't have bundle diameters defined yet. We can make use of automation to calculate the bundle sizes utilizing our wire library definitions. Now we are ready to pass back our updates to NX. To create bundle solids in NX based on VeSys data, create bundles during route list import needs to be enabled. Following the export, bundle solids have been computed using diameter data directly from VeSys, and wires are added to the electrical connection navigator. The bundle, or in this case of NX, stock, diameters are populated and the splices are placed automatically based on their locations in VeSys. Again, cross-probing helps verify the data came over correctly. It is also possible for the mechanical designer to make modifications to the splice positioning that can then be sent back to VeSys. Preserve electrical content will be used during bridge-in, so all the Ecad data in the existing design is added to or updated, but not deleted. The splice has been moved to its new position. The mechanical engineer now has accurate bundle diameters and splice positions to work with. They can proceed with interference studies to determine if the harness will successfully fit within the target application's enclosure. If updates need to be made to the 3D harness, the changes can be easily passed back to VeSys to update the design. Through the course of this demonstration, we have explored the various integrations between VeSys and NX, exchanging both wiring and harness data. The underlying advantages provided by Ecad MCAD integration can be found throughout the flow, reducing errors, speeding up design time, and enhancing collaboration between both domains. In closing, I would like to return to the question we started with. Why is Ecad and MCAD integration necessary? It is this type of integration that supports the development of mechatronic products that are growing in both demand and complexity. The increased visibility between domains is critical for cross-functional design teams to maximize efficiency. The automation and the handling of this data exchange gives designers more time to focus on validating their designs and innovation, both of which improve overall design quality. With both electrical and mechanical portions of the design being of equal importance, fully understanding both aspects will in the end result in a better product. If you'd like to further explore what was presented today, I would like to invite you to download the new VeSys trial that has been recently created. It can be accessed at trials.sw.siemens.com/hyphenated free trial wiring harness software. The trial will give you full 30-day access to VeSys and include quick start videos and data to help you get up and running. I hope you found this presentation of interest, and thank you for your time.